已解锁，请取出话筒。
Okay. All right. Let's start. So if you recall from general topology, right, we can check that two spaces are homeomorphic by using connectedness and compactness. Do you still know how to prove homeomorphism using this? Two spaces are homeomorphic. If you have a connected space, you apply homeomorphism, then the image is still connected. If the space is compact, the homeomorphic image of compact set is still compact. Okay, so these two properties are preserved by homeomorphism. Okay, so another thing to see was if there are two spaces is not homeomorphic, then you can see that one of them is connected and the other is, or one of them is compact and the other is. Okay, so today we're gonna learn a higher level way to show two space is not homeomorphic by using Taiwan. Okay, fundamental. Okay, so this was the corollary we left last time. So for every n not equal to 2, actually R2 is not homeomorphic to. Okay, so how to prove this? Well, a very standard way is suppose that there is a homeomorphism. Okay, to use contradiction. Okay, so if we have a homeomorphism, what's the thing we do last time? We can remove one point. Right, we remove an image. Okay, so for the case of n equals to 1, what happens? On one side you have R2, and on the other side you have R. Okay, let's say I remove one point here. Okay, remove the origin. Then under this map here, I should remove one of the point here. Okay, so what happens? So this case is easy. Okay, on one side you have half connected space. On the other side, you cannot connect. Okay, so in this case here, this is pretty obvious. How about n greater than 2? Okay, so when n greater than 2, then things become different. Okay. So for example, I draw R3 here. Okay, if you remove one point here, and then you remove another point here, okay, still connected. Okay, still connected. So how to distinguish? Any idea? Any idea? Okay, so the key here is to see that this Rn throw at one point is homeomorphic. Sorry, yeah, it's homeomorphic to x n minus one s minus one cross R. Okay. For those who see algebraic geometry before, you should be familiar with this. This is like the RPN. You project this space. Okay, so how to think about this? Maybe I look at R2 cross R here. So how do we study this space in particular? So how do we study was we just consider all these parts. Okay, you think of a ray radiating radially, okay, from the point you remove. I mean, for the sake of simplicity, you can think of it as the origin. Okay, you can think of it as the origin. Okay, so you see there's so many R here, real number. So where's the Sn? So here, okay, so in this case here, our claim is S1 cross R, right? So where's the SR here? SR here basically is referring to I have a circle of R. Okay, so this generalized to a higher dimension. So I suggest you to write down this. Yeah, I suggest you to write down this homeomorphism here. Or not? Yes. Question? Yeah. 嗯，yes，对，没有错，对。If you don't delete, then you have something extra. You have extra point. Okay. Yeah. In the RPN case, we also delete the origin, right? Yeah, otherwise, it leaves like all the equivalent class. Okay. So. Okay. Yeah. So another way to think about this is like you. I think I got a paper today. Yeah, imagine this is the Rn. Okay, but let's say I pop it. Huh? Because we got a homeomorphism. So I pop a point here. Yeah, I pop a point here. Can you imagine that if this hole become big, actually it's a cylinder. Maybe I can like open it up. Huh? Right. Right. Open it downward. Imagine or not? Okay. Can you imagine? I cannot pull this, unfortunately. Maybe I can pull a little bit. Right. Does it make sense? Does it make sense? Does it make sense? If I have a clay, then maybe I can pull a bit downward. But can you think of this as an elastic material? Can. Okay. Yeah. Well, try this. Yeah, you can try this. Make it a little bit. Yeah, yeah. Okay. I'll try this. Okay, yeah. So actually, this is the origami class. Sorry, not math class. Okay. Next. But what's the pi one of this? So, pi one of Rn throw away a point. Okay, is actually homeomorphic to pi one of xn minus one cross R. Okay, but we know that the pi one of the product is product of pi one. Which one? Okay, and then what do we know about pi one of xn minus one here? Okay, first of all, pi r1 of R is just trivial group. Okay, so we get back our pi one of xn minus one, okay, because Rn is contractible. Okay, this is trivial, as R is simply connected, like we talked about in the quiz last time. Okay, but what is pi one of xn minus one? Okay, so this is only equal to z when n is equals to 2, but 0 when n is greater than 2. Okay, this is what we have shown last time. Okay, but we also know that from the I put it under the functoriality of induced homomorphism, that homeomorphism actually induce induce an isomorphism on pi one. Okay, so if you have different n greater than 2, which is greater than 2, you are 0, so z cannot isomorphic to 0. Okay, makes sense? Question? Okay or not? So one group is big, one group is trivial, so they cannot be isomorphic. Yeah. R, when n equal to 2 is Rn, R2, so pi 1 of x1 is Z. This is what we have proven last week. Counting how many circles. Okay. Yeah. Okay, so today I bring a torus. Actually, it's a set of 10. Okay, you can think of it as a torus. Okay, so I also bring 2 loops here, or rubber band loops. Okay, so one is the meridional loops, which is one of the generator of Z cross Z. So you can think of it like so you can think of this loop and circle around this torus externally. I mean, it's always externally, but let's call this a meridian circle. So you see this meridian circle can always stay on I'll say the surface of this torus here. Can you imagine or not? You can go in, go out like that. But you can never like pass through the handle. We call it handle of this torus here. Okay, cannot pass through. Okay, so what's the way to pass through? Is it cannot pass through? I want to like slip this rubber band around this torus, not meridianly, but this way, longitudinal circle like that. Can I put it in? Can? If you can, please tell me one day. For now, I don't know how. Cannot. Okay, one way to do it is to snap it. Snap it. This is still continuous. There's one point is not continuous. Not continuous. Snap already. Okay, so but I can tidy it up. Yeah, let's tidy up. So this is like not continuous already, but now it's still continuous. But when I join them, it's not continuous anymore. So in this case here, I got this longitudinal loops again. Okay, so this one can circle around this horizon. Okay, but it cannot become the meridian again unless you untie it. Okay, so these are the two generators for torus. Okay. Yeah. Okay. Right. Okay, let's continue. So last week we talked about retraction. Retraction is just a map that you map into a subspace, okay, of your space, such that your map restrict to that subspace is identity. You don't move anything within the subspace, but anything outside the subspace, you try to send to that subspace. Next, we're going to introduce something called a deformation retract. Okay, deformation retract. Deformation retraction here. Okay, so this is not retraction, but it is a homotopy to a retraction. Okay, so please don't confuse that. Deformation retract is a homotopy. Okay, homotopy from the space onto a subspace. Okay, onto a subspace A is a homotopy. Okay, homotopy from where to where? So this makes the definition quite important. Is it ready yet? Your exercises ready? Next week, right? Yeah. Yeah. Please finish it this week. And how about the week 2 draft? How is it going? Typing or not? Still typing? Please finish by this week, yeah? The template is already online. Okay, you can use it. Okay. The deformation retraction is a homotopy from the identity map. F of X to a retraction. Okay, such that for every T, Ft restricted N is identity. Okay, maybe I give some short definition here. Let me define homotopy between maps. F and G, okay, from X to Y. Well, it is a continuous map. And let's call it H with X with some timing. So you cross with a unit interval to Y. Such that F of S X of 0 should be, let's say, F X, and then H of X1 is GX. Okay, maybe people can try and check it out. So this is the general definition, okay, between homotopy between maps. Okay, so what you require was you have two maps, okay, and then there's a timing where you do this map. Okay, so when you start, you should start with the first map. When you end, you should end with one map, the other map. So in this definition here, there's an extra condition here. Okay, so we have a retraction condition here. Similarly, for the path homotopy, right, you also have an extra condition for the path. So you require for every time, every starting point, it is the path that start with the same endpoint, and at the end time is the same terminal point. Okay, so there are some extra condition. So you need to see it is a homotopy between what thing. Okay, maybe that map will give some extra condition for your homotopy. In general, we just require that when you start the homotopy is the first map and the homotopy is the second map. Okay. In this case here is very also very interesting. You see, Okay, we know that retraction F restrict to A is identity. How about the starting point identity? It's still the same because identity fixed even more things. Okay, so the homotopy we study here is quite restrictive. It's not like you can change all the way and then come back retraction. No. Okay, is you still keep the identity on A and then you slowly do your homotopy around, outside A. Okay or not? Okay. Yeah, it's not just random homotopy. So this is what we call a deformation. Okay, deform. Okay, so you deform to a retraction. Okay, so let's put a remark here. One truth is not all retraction come from deformation retract. Okay, so you could always have a retraction, but you might not have this kind of homotopy, right? Because the requirement for homotopy is continuity. So you need to make sure the continuity work. Okay. So what kind of retraction doesn't always come from deformation retract? So for example, you just retract a space. Okay. Retract a space to. Okay, now this is not always true. Maybe this picture, if you see as a this is true, but it's not always true. Huh?
I cannot imagine.
You should okay, so the point here is the point here is like this is the counter example, right? I don't consider it as a, so I just consider it as S1 union some other point. This is zero. Okay. Yeah, you can try show that the retraction of this x here to this point is not a deform. This is not coming from the deformation. Cannot, right? Yeah. So how to show? Maybe you show, suppose there is. Okay, later we will deduce more how to say, more property on deformation retract. Then maybe you can use those property to see why you don't have this kind of retraction. Okay. Okay. In particular, the next one is useful already. So this is also useful for your assignment as well. If a topological space X, okay, retract onto subspace A. Okay, so imagine your space X retract to a subspace A. Okay, maybe I draw it a bit bigger. I don't. Okay, then the homomorphism induced by I star here. Sorry, induced by I. Sorry, this I star is an induced homomorphism by I, which is the inclusion. Inclusion is actually injective. Okay, makes sense or not? Think of it, makes sense or not? Okay, so if you have a big space X, okay, you want to retract to A, so you retract to A, right? So you have a loop in X, and then you, by retraction, you send it to A, okay? So that loop could stay as a loop, or it is not loop anymore. But the intuitive idea is it should be able, I should be able to like get this small loop, loop in the small space from this large space, right? Because A is part of X, A is part of X, right? Okay, so every loops in A should be a loop in X. Okay, but the point here is this is injective. Okay, it's injective. Okay, we didn't like identify any two different loops in A. Okay. So when is it an isomorphism? If A is a deformation retract. Okay, so meaning you have a homotopy, okay, of this for this retraction, then this inclusion here is actually an isomorphism. So what's left here? What's left is surjectivity. Okay, why surjectivity will work? So every loop in X become a loop in A. So you must use your homotopy. Okay, use this homotopy to help you to find the loop. Okay. Okay. So this proof is pretty straightforward. Huh? Okay, so let's quickly discuss this proof here. So first part, suppose Rx to A is a retraction. Okay. So then you can consider this map here. Ri equals to identity. Okay, we always want to relate back to inclusion now. The inclusion map. Okay, so you include and then you retract back again. Still going back to A. Make sense, huh? Make sense or not? Okay. I write down I to X, X to A. Okay. But then by the functoriality of induced homomorphism, what do you get? R star, I star is equals to identity on fundamental group. Okay. But then this says what? R star has a right inverse. So anything with a right inverse is injective. Okay. So sorry, wrong way. Right inverse, because we want to deduce for I star. I star have a left inverse, then I star is injective. Okay. You can go forward and then come back. It's a one-to-one. Okay. Can you remember this left-right thingy? Yeah? So this semester I was teaching this. So let's say this is I, right? So let's say A1, B1, and A2, B2, B2. Okay. So if you can go forward, okay, go forward, one-to-one function, you can define an inverse. Okay, which by reversing the arrow. Okay. It's enough to define on the range. Because when you compose, right, you will only meet the range of I star. Okay, no need to require subjectivity here. Okay, so I star is injective. Okay, how about second case? Second, I want to show that I star of pi 1 a x naught to pi 1 x x naught is surjective. Surjective. Okay, so meaning I gave you one loop in x naught here. How do you produce a loop in pi 1a? Obviously, you need to use the deformation retract. Okay, so suppose you have a deformation retract. Suppose RT from x to x.是要讲梦话 So RT is a deformation retract of x. 什么情景？要不要学一下你的情景？给你讲一下。Okay, so what's this reformation retract doing again? So when R naught is identity, okay, for every time restrict to A is identity, also R1 of X live inside A like that. Okay, so this is the condition. So can you use this RT here to build a loops in A? I mean, there's something that map to A, right? Another key point here is this 2x1 is the same. Okay, so you are safely to use this R maps here. Are we safe? Yeah, because this x0 is in A as well. Okay, so we are safe. If x0 is other point, then we need to maybe do some conjugation or something like that. Okay, well, you can consider this R1 gamma because R1 will map your x to A. Okay. Moreover, actually, these two are the same loop. I mean, they're same. Meaning, meaning, it is same here. Okay, these two are the same loop. What's the homotopy in pi 1x? What's the homotopy here? What's the homotopy? Yes, just RT gamma. Okay, just apply RT gamma here. Okay, so in this picture, how should you imagine? So maybe here is your S0, right? And then your path maybe looks like this. Okay. Then using this reformation retract, maybe you retract. Is this the way to retract? Maybe retract. How to retract? I don't know how to retract, but maybe somehow you could make it into a loop inside A like that. Got idea? Any idea? You mean just like this? I don't know how. I don't know, but yeah. Again, imagine there's a homotopy. So what kind of homotopy should we have? The homotopy here is like I don't know. Maybe I think we should write down a homotopy first. I think the homotopy should look something like this. Just like squeeze everything to one point. Make sense? Does that make sense? Okay. Yeah, I think this depends on the deformation retract you take. Okay, so it depends. Okay, I don't know how it retract. For now, I'm not sure what's the possible way. Can I just stand like that? Yeah, but anyway, I think we should write down first. Only we know this. We need to write down a specific one. But I don't have a specific one in mind. Okay. So what can we see here? Remark. So in the fixed points theorem, okay, in the fixed point theorem, we already somewhat see that x1 is not a retract of d2. And from the above proposition, we also can show by looking at this inclusion induced map. Okay, which is z to 0. So cannot be injective. Okay. There's no injection from z to 0. This map must be a 0 map. Okay. So this is how you show the question, last question in your assignment 1. So what you need to figure out is their pi 1. Okay, there's one thing you need to learn to find is what is pi 1 of x1 wedge x1. Hopefully we can cover it today. Depends, see how. Okay, any questions so far? Any questions? Okay, next. There's a student actually missing again. Not Hao Tian. Hao Tian, I don't know why missing. Another one. Okay. Han Wei. But Han Wei is on duty this week. So, should we think of replacing him first? What do you think? Maybe if he get better, he can do the later one. What do you think? 啊，你跟他换啊？OK，你可以先换。I'm not sure 下个礼拜他会不会比较好，depends 啊。如果你愿意提早，OK，那你做这个星期，OK，OK，说精神。你愿意什么？What？ Okay, so next definition, best point preserving homotopy. Okay, you see, this is another homotopy. Okay, this is a base point preserving homotopy. So what happens here is we are allowed to look at different base point now. Okay, but under a condition that you want to guess what's the condition here? You want to guess? Don't want to guess. Hey, so what's the relationship between S naught and Y naught here? Huh? What's the relationship with one on X and Y? Can they be different? Okay, they are different, but there should be some link here. We cannot simply put, fix that point. So what do we mean by fixing that point? So actually we require for all time, our homotopy must send X naught to Y naught. Okay. So it's like the case like, if you have a loop on X naught here, okay, this is on the space X. So we can shift between spaces now. Okay, so this is Y naught. But every time you send, okay, S naught must always going to Y naught only. Okay, others don't really care first. Okay, as long as continuous. Okay, so one proposition is if phi t is a base point preserving homotopy, then the starting and the ending point is the same induced map. Okay, starting ending point, I mean the starting of homotopy and the ending of homotopy. Okay, so how to show this? You want to check induced map, right? Is the same. So it is a map on fundamental group. Okay, so you just check on every loop. So okay, you just check on every loops. You just check on every loops so that they are the same. But but how do you add on loops? Is you just do the loop and then you map it across. This is exactly what the induced map doing. Still remember, I to X, X to Y. You do IX and then you do XY. Okay, same on the other side. But are these two the same or not? These two are the same or not? This is starting point, this is ending point. What's the middle? Huh? What's the middle? These two are the same loop. Why? Because you have a homotopy between them. Okay, because these two are homotopy. Okay, what's the homotopy? It's exactly phi t via phi tf. Phi t is a homotopy. Makes sense. Okay. Okay. So far, so good. Okay, so from here, we'll continue to define more stuff. So this is a very important, one of the very important definition in our class. So there's a special type of continuous map, which is called a homotopy equivalence. homotopy equivalence if there exists a continuous map such that Fg is homotopic to identity and Gf is homotopic to identity. Okay. Not equal anymore. Here now it's a bit different from the lower form of mathematics. You just check equality on function, but now Fg might be something else, but as long as homotopic to identity, that's fine. Yeah. And so you have an extra thing coming out here. Or you have an extra thing coming out here, which you require. Okay? Does it make sense? This definition is very important. This is how this subject here can go to a more abstract direction because of this non-equality here is pretty important. This is also an idea governing category theory or categorification. And we don't care about equal anymore. We care about equal in the index space. And maybe in vector space is about isomorphism. And maybe they are not the same vector space. As long as they're isomorphic, that's fine. Okay. And moreover, this homotopy equivalence here, we will abstract this idea from topology, okay, into algebra only. Okay. So in the category theory, we also have a definition for homotopy equivalence. Okay, there's no more topological space in there. Okay, we will see more when we introduce homology chain complexes. Yeah, we will see this in a more abstract form. Okay, then if this happened, we'll say that the topological space XY are homotopy equivalent. Okay, homotopy equivalent. So this is a very standard terminology, right? Okay. How equivalent they are homotopy equivalent. Or if you look at some popular science or popular mathematics article, you might see this term here, which is a homotopy type. So they are of the same type, so the same homotopy type, and we will denote X as homotopy to Y. Okay, so I think in GT we also use this for homeomorphism. Okay, homeomorphism is slightly stronger than this. Okay, so if you can imagine homeomorphism, what happens? It is not homotopic, it is just equal because there's an inverse there. It's just equal. But I mean, identity always isotopic to identity, right? Sorry, identity is homotopic to identity map via the identity homotopy. Okay, so should we change notation or it's fine? Is everyone happy? Yes. Sure. Sure. I'm not sure if it's on top of my head or not. It's not homeomorphic, but same homotopy type. I'm not sure if it's on top of my head. Maybe you can think about it first. I'll let you know. Or if you found it first, you let me know. Yeah, maybe try think about it. So you need to think about a homotopy equivalent that's not coming from a homeomorphism. Okay. I'm pretty sure that is. Otherwise, it's useless, this definition. Otherwise, there's an if and only if statement. Correct. Okay, but it's not the case. So I think that is. Okay, but we need to find out. Okay, so maybe we put a question here. We can go and find out. So any two spaces that are not homeomorphic. So you might think you need to think of the not maybe one of them connected or not connected, or one of them is compared or the other not compared, or yeah, pi one is different. But but deformation. Can I say of each other? I think can be each other. Sorry, no. Homotopic. Homotopic equivalent. Okay. Okay, maybe we will discuss more property on homotopy equivalent. Maybe can shed more lights on this question here. Okay, this is a pretty good question. Okay, next definition is we finally want to define what is contractible. So we'll define it on topological space. Okay, so if a topological space have the homotopy type of a point, okay, so meaning it is homotopy equivalence to a point, then this space is called contractible. Okay. So proposition, I think this one is easy to prove. We won't do it here. So topological space is contractible if and only if the identity map on X is now homotopy. Okay, I think this is pretty straightforward. Okay. Maybe just left as an exercise. Okay. So this one left as an exercise. Okay, second, let's look at some textbook examples. So for this statement here, if a space X deformation retract okay, onto a subspace okay, via this homomorphism here. Okay, then what do we have? Then actually we have Ri equals to identity. This one is pretty obvious. You just include and then retract. And then on the other case, actually we have retraction and then inclusion. It's not identity, okay? It's not identity because you retract from X to A and then you just identity to A. So this is a map from X to X. Couldn't be identity because your image only got A. Okay, so but it is homotopic to identity. Okay, so how do homotopy to the identity here? So you need to think of like the identity of X. You shrink the range, shrink until A. Okay, how to do that? Okay, you cannot just compose with any function, but instead, you should think of it as another layer to connect these two. And then this layer is via the homotopy of map. Okay, via homotopy of map. Okay, does it make sense? So when you think of this homotopy, right, you should think of it like last time I give you an analogy of tables, right? One side is a map, the other side is another map. And then you should think of this homotopy as like connecting these two maps. Okay. Yeah. Okay, another higher subject to talk about this thing is called cobordism. Okay, you can find it cobordism or Bodism. Okay, so literally our space is like built up by these things. Okay. Okay. So in this case here, what we have proven is actually X is a homotopy equivalence to X deformation retract. Okay, as long as you have a deformation retract, then we will know that these two spaces are homotopy equivalent. Okay. Okay, so let's look at this space here. If you still remember this two space here. Okay. This is like the topology of 2 points. Yeah. Okay. Topology of 2 points. There are few deformation retract you can do here. Can you think of any deformation retract of this space? Okay, the space we are taking here, by the way, I need to tell you first. Otherwise, you don't know what place I'm taking here. Okay. So a deformation retract to what? Can someone give one deformation retract space? I'll try. Then you want to try or not? Huh? No idea. Okay. Jason want to try or not? Some subspace that it can retract to. Huh? Boundary. Boundary. So how is it the boundary looks like? You mean this boundary, this boundary. This boundary like that? Okay. Mm, but but what? But but then what? But then there's no homotopy to this boundary. How to say this? If you try to write down the map from this orange part to this blue part, right? You should think of like there's some point you must like split. But this deformation retract, maybe retract can, retraction can. But we want deformation retract. Okay, so you cannot like splitting out. Right? Sorry? Half, what do you mean half? Cut? Cut where? 剪哪里？怎么要剪掉？剪哪里？剪啊？这样剪？怎么剪它？剪了怎么？啊什么？什么？怎么要剪它？我不明白，怎么剪它？so you mean 啊？诶，可以唱，差不多。没有累啊，我这边唱不掉，那这样怪怪的，干嘛不给我唱？这样哦，真的唱不掉。Okay, so maybe let me redraw one. So you mean retract 去这样子一半，一半，这样子哈，是这个吗？But but 你又有一个绕着那边的东西被你垄断了，对吧？你这边的东西一定要被你拆断才可以进这个 retraction。你可以明白我讲吗？You see, there's some point here, right? This close neighborhood point, right, must be split to retract to the subspace. Okay, so there shouldn't be some homotopy here. Okay, it's a retraction again, still retraction, but not a deformation retract. Okay, so 还有什么可能性啊？至少哦，那个书有3个答案在那边，你至少应该也要中一个吧？你看剧透，OK，我们接受剧透。Infinity. Okay, so maybe you can do something like this. Okay, so it's like the outer one going to here, and then the inner one go to this middle string here. But there's another different one, okay, which is called a dumbbell because it really looks like a dumbbell like this. Okay, it's like you pulling the intersection a bit longer. Okay, Another one is, I don't know what to call it. Can you give it a name? Spider-Man. So you extend that intersection on the other way. Okay. 什么东西 mitosis 哦，有点像哦，确实有点像。Okay, but if you separate these deformation retract out, right, they are not subspaces of each other. Oh. You cannot find one of them is a subspace of each other. Can you recognize? Because this one don't have this straight line. And then these two circles match in wedge in one point, but this one no, so not subspace of each other. And then these two also not subspace of each other. Don't have this vertical now. Both of them. Okay, so you can deformation to a subspace, okay, such that these subspaces are not deformation retract of each other. Huh? Yeah, yeah, then. So they come from the same place, but they are all different. Okay, different in the sense of deformation retract. Maybe you can define another sense. Maybe they are the same, but for the moment, these three are not, but they are not. These three are not deformation retract of each other. Okay, but they are homotopy equivalent. Okay, although they are homotopy equivalent because they come from the same space. Okay, they come from a deformation retract of the same space. The equivalent. Okay. So you might observe for now, homotopy equivalent is like Taiwan. Almost like Taiwan. So here got two circle, here got two circle, here got two circle. Okay. But you cannot deformation retract to it. Okay. Not even a subspace now. Don't talk about deformation retract. It's not subspace. Okay. Okay. So one proposition. I don't want to say left at the exercise because one direction is pretty hard for now because I haven't defined something yet. So you cannot prove it. One direction is easy. So any two subspace are homotopy equivalent if and only if there exists a third space, another larger space, okay, containing x and y as a deformation retract. So the direction from right to left is what we have demonstrated just now. But left to right is a bit complicated. Okay, we haven't described this construction yet because from left to right, you need to construct this Z. Okay, so maybe construct this Z, you need to form something called a mapping cylinder. Maybe I will introduce later when we really want to use it. But or if I found the proof, I can put it in also. So what's the mapping cylinder? Anyone read actual chapter 0 already? What is the mapping cylinder? Okay, kind of. So you can think of x and y. Okay, you have a map from x to y. So, well, I mean, in the calculus class, right? What you would know is like I got an x here, and then you got a y here, right? And then I mean, even in the abstract algebra, I draw something like this, right? But the shape could be something different, right? Okay, depends on your map. But then, but then, but then, if you include this line into it, it's what we call a mapping cylinder. Okay, so this line is a 0 cross 1. Okay, so you just step x, and then at the last point here, you become something weird. Okay, and then this part you glue to y. This is the mapping cylinder. So this cylinder here, kind of like cylinder, is come from mapping. Okay. So this is done. Okay, this is if you flip this side, it's a cylinder. Yeah. Full elastic. Okay. Right, cool. Okay. How about let's take a break here. Any question so far? No question? Yeah, if no question, let's break for 10 minutes. Let's come back. 10, 8 minutes. 什么？OK。没有。
不好，
做不好，
都会好。
找其他 reference 咯。课本不好咩？惨啊，当然了，我们就要来一步一步看啊。
那我还想着来去
嗯，
看不到，有些人可以，就是看起来还又有用哦。看，我发现到它有2个解释，
什么意思啊？
有2种方法
解释什么？
看东西哦。
OK。
他来讲什么？就是什么 frame，还有一个要用 color 去塑造。
Color quotient space。
哦，讲这个 color quotient 一提出来，
OK，要看一下，
是哦，然后
要 define 一下。
有东西不对了。那个地方我只发现它是有用很多这个东西。有点，就是它发现差不多可能。那刻骨为根在那种讲，
你要直接去搜那个字诶。
他说那不如去那个铁一看，第一个还是有几个啊？
对，所以就要来找一下从哪里开始看，然后肯定是要来一步一步看的，不能够来一下子就。我现在重点是你要 identify 什么要读比较重要，那我们就一步一步读，不可能一天就读完了，对不对？呀，但是你可以在一天内知道你要读完什么东西。So I mean 是来什么 definition 很重要，要从哪里看下来？对啊。他们讲蛮贵啊，有些人吃到不合胃口，不舒服。还有它的粥是放生蛋的，然后他们讲它的那个粥不够热，然后而且那个蛋可能放外面很久，因为马来西亚人很容易坏，所以不是很明显。不习惯的人会觉得很难吃。够热那个粥。
哎，还有今天啊，那个 V 三好哎，
对不起，
不可以，今个礼拜一定要出，今天就要出来了。今天要出炉了，一个下午的东西嘛，好的。
帮我给他们送，要帮我收回来。哎，艾文就失踪了，真是的，有几个每次艾文有生病，还没有好没？不是好了没？人上两代，
我拿9.5，
你看一下
所以扣我0.5。
，OK 没有在，
R is contact 不是很特别。
等一下还给我啊，看一下。 红色是我的啊。诶，下次你们改的时候不要用红色啊，可以用其他颜色。这样我可以用红色，不然我就要用其他颜色。你可以拍起来，要还给我啊，这张纸。OK 啊，看得懂吗？
看懂啊？
不知道要写什么答案啊？不知道啊，不是大概哦，那考试会扣分哦。
二是考那才要仔细看。
就是来，
你可以先。
我怕你写不出那个equation，因为你两句话都没有equation，所以我怕你知不知道你在讲什么。你讲的东西是对的，但是来，有些人是啊，不是不够用，就是说在这个课里面肯定是我们要你学一些 mathematical 的 expression 嘛，对不对？对，所以这两个你都要会啊，就是那些 linear 和都 linear。Yeah, so I put a full solution on the Moodle already. So if you want to check, you can check. Okay? Come on. 不知道。
那你是什么病？
生病呢？等下有事情做，还没跟我讲生病。
那你当时
他应该好。
快点事情做。OK，还有时间。哎，这个生病很严重，你知道，中学已经黄掉了，有些中学有那种住宿学校全部关了，全部传完。然后在讲什么？老师哦，很多
我病
很多都关了，流感的那种。
那那时候你做一个分照，我吃饭啊，然后我没有中嘛，因为我因为是赔钱了。
是哎，
他中那个购物币的不是？购物币的，那你有那医生讲，过后你要生病了，然后就我们
你陪他去看医生。你是医生的 outlier。Okay, after you see the quiz, you can give me back. You can take picture. All right. So let's say 5t is homotopy. Obviously, here we are talking about base point preserving homotopy. Just that we are quite lazy to draw things. 懂我在讲什么？ Because now space already changed. You should understand that the base point could be changed. Okay. No longer you are living in the same space already. Okay, so actually the homotopy we are talking now is the base point preserving. Okay, and H is the path of 5t x naught. Okay, let me check. Okay, right here as not from images. Of base point x naught x here. Okay, then we have the following commutativity diagram. So pi 1 of x naught. Okay, go to 1 star, which is pi 1 y1 naught. And then the other one, we can go to pi 0, 0.50 star, which is I1 of y at 50x0. And then these two are the different, could be a different base point. Okay, but what we can do is we use the half that connect these two base points and then look at the induced map from this path here. Okay. Actually, this H star is the beta H in your textbook. Okay. This H star is the beta H in your textbook. Also is the one in your assignment. Okay. It seems like this homotopy is not quite the base point preserving homotopy. It is not the base point preserving one, this one. Because otherwise 51 x naught is just 50 x naught. Then this H is just an identity. It's just a constant map. Okay, so this is not quite the base point. Okay, so the base point preserving use where? Why suddenly introduce this? Okay, we'll figure out later. Okay, so how to do this? Basically, is quite straightforward. So how is it straightforward? So what do you need to show? Just write down what you need to show. I think it's pretty clear what you need to do. So you have to apply this H0 star to a loop, and then apply the other composition to a loop. Okay, so you need to show these two are the same. Okay, so basically you are showing two paths is the same. Okay, but why these two loops is the same? You need to use homotopy, right? Okay, so what sort of homotopy you should use here? So on one side, you have a 50x0 point with a base loop here. Okay, another loop is looping at 51 of x0, and then this is a 51x. So what's the homotopy between them? But you have a path between these two. Is it these two? Yeah. So this is the path. Okay, so all along these are base point of some other path. Okay, so can you think of a homotopy here? Can you think of a homotopy here? Can you think of a homotopy here? What? So you see, first of all, are you agreeing that these two paths live in the same space or not? You must understand that these two paths live in the pi1 of 50x0. Okay, so one of it is obvious because 50. The other one is 51. But 51 is based at 51x0. But your image is based at 50x0. So how do you connect? You connect using this H, right? Because you use H to go up and then loop around and then go down. This is the conjugation map. Okay, but the point here is how you do a homotopy from here to this one. This is a bit like university. You can loop around here and then do what? Where's the homotopy? How to go from this to this? You cannot jump straight away. You must do slowly. How to do slowly? You need to remember every loop, there's a loop here as well, which is a phi t to f. Can you use phi tf to build a homotopy between these two loops? You cannot straight away go up, but you can go out a bit, and then do this loop, and come back. and then go further up a bit, and then do the loop, and then come back. Okay, so your homotopy is like 5t, sorry, ht, and then do the loop, and then come back. So when this t is 1, then you go up all the way up, and do the loop, and come back. When t is 0, then this is a constant loop. Stay here, do the loop, stay here, and do a bit, 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 do a bit. Okay, then you fill out this space already. So homotopy. Okay, it's continuous, right? Because everything you do is continuous. Okay, question? Any question? Okay. Okay. Next proposition. Okay, now this is a very important point of homotopy equivalence now. So if you have a homotopy equivalence, then the induced homomorphism is actually a isomorphism. So phi star on pi 1 of x, x not here, go to pi 1 of y, x not here, is an isomorphism. Okay, for any base point, okay, regardless. So how to show this? Okay, this proof is a little tricky. It's a little tricky. So okay, so proof. Okay, by assumption, we have so okay. So how about no? So let's call okay. We have the name already, right? So okay. How about the other direction? Let phi. So what is this psi? Let psi from y to x be the homotopy inverse for phi. Okay, such that phi psi is identity and psi phi is also identity. Okay, but identity is not equal. It's a homotopy only. Okay, homotopy. But this is enough. Okay, this is enough. So let's consider this chain of maps here. Okay, let's consider this chain of map. So we induce a map on pi 1 from pi 1 x to pi 1 y. Okay, and then psi induce a map from pi 1 y to pi 1 x back, but the base point change to psi phi x naught. Okay, how about the other direction? We have phi star again. So we will go to phi psi phi x naught like that. Okay, let's look at this change of map here. All right. So let's look at the first identity. So first composition. The composition of first two maps here. Okay. So what does it mean here? Okay, so note that phi star, sorry, psi phi is identity. Okay. So this implies what? What does this imply? What does this imply? Injective, more than that. 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 Okay, so these two are homotopy, right? So just now, what do we know about homotopy of between maps from previous we call it lemma. Okay, so if you look at this phi star here, it is equals to what? Equals to a half conjugation, okay, on the identity. Okay, just now, from just now. Okay, but then H star is isomorphism, right? On the other side, you have these two composed, the induced map composed together. So what does this mean? This means that the composition is an isomorphism. Okay. So here implies that differ by a half induced path isomorphism. Okay, so this is your, just now we got the phi 1, right? Here is the phi 0, okay, in previous lemma. Okay or not? Make sense? Does it make sense? Okay, because you see you potentially change your base point already. So, but there is a path connecting H. Okay. I think this one we showed last time. The H star map is an isomorphism last time. The base point change. Yeah, that one we showed it last week, I think. Okay. So similarly, so in particular, so since phi star, psi star is an isomorphism, who is injective? The right one is injective. So use the same logic, okay? You apply to the third and the second and the third one. We can see that. With the same logic, we can see that psi star is also injective. Okay. So are we happy here? So these two are injection. This one injective. And then this one injective. And their composition is isomorphism. Now we want to claim that this one is surjection. Is it possible? Let's write down. So phi star is psi star injective. And then phi star psi star is isomorphism. I think the other way we also know is isomorphism. Can use from these two to say that psi star is injective or not? Sorry, surjective. Any idea? Can we know that? Okay, so injection is left inverse, right? I can go there and then come back. And then surjection is a right inverse, okay? So meaning we need to find a right inverse for this guy. Okay, so where to find the right inverse? Huh? So I think potentially here, because here right side got something. Okay, can we find an inverse for him? Let's try. So let's do some working here. So 5 star, 5 star, 5 star is some isomorphism. Okay, because it's isomorphism, right? There should be an inverse. I think we are good. So we just put the inverse here. This. Then this is the identity. Then this is your uh left right inverse, sorry, right inverse. Okay. Okay, not okay. It's just algebra trick here. There's nothing special here. Okay. So far so good. We have finished, finally finished this subsection here. Yes. Why do you need one? Best change? Best point change? Why do we need that change? It's just a convenient way to talk about composition. Yeah. Otherwise, you need to say I change direction. But another thing is another thing. Yeah, nothing. I think that's the base point. That's the main point. I think it's easier to talk about composition in the two ways. But not. Otherwise, you just say swap direction. It's the same thing, I think. Yeah. Yeah, it's just a convenient way to talk about it. Yeah. Later you will see a lot of chain complex already. Now you just okay. Yeah. Okay. Good. Good. So now we're gonna go into one very important theorem in your life, which is Van Kempen theorem. Okay. Today we won't prove it. We will talk about some motivation and then hopefully some examples. We'll try to discuss proof on next class. The proof is very, very, very technical and tedious. So we also won't attempt to write down the proof in the class, but we will talk about the main idea. Okay, okay, not yeah. But I suggest you to read it once first. Okay, so that you can understand what I say. I will put out the note today as well, so you can read first. You can read the art. You can read the actual one. You also can read mine, and then see what's their relationship. Okay, so the slogan for this group, for this part here is, for every group, there should be a topological space, called it xg, such that the pi1 of xg is g. Okay, so this is very powerful because you can realize any group as a topological space. Okay, such that the pi1 is g. Okay, now this is what the nail. No, the nail of this course comprises even more. This is just part of it, just one main part of it. Okay, so actually you can teach abstract algebra on using topological space. Okay, so this one even more general because there could be different topological space that have pi1 as g. Not equivalent. Unless you maybe can or not. I don't think you can recognize. Never mind. I think not equivalent. Okay. Yeah. Okay. But the key technical thing is I want you to recall is I don't know, go to your mind and then pick this thing up. This technical point here is called a free group. Please pick up that subtopic. Free group. Okay, you remember? Make sure you remember everything. Okay, we're gonna use everything there. Please pick up this free group here. Okay, so if you want to recall, we got a note, so you can use my notes. Yeah. Okay. Okay. So far is these. Okay. So motivation for the next definition. So this definition is very different. Okay, we have a bunch of groups. We want to put them together, but it's not like a product way of putting them together because product way is not efficient enough. Okay, so what we want to do is you should think about this. I think this is quite an ancient construction, but it is very, I'll say, intricate, very intricate, and then but it makes it how to say, it makes itself survive in the history. Okay, usually this kind of definition I'm gonna throw away already, but this guy luckily survived. Let's see why he survived. What's the importance of this definition? So the point here is we want to construct a single group that contain a collection of subgroup. Let's call it G alpha. Okay, you might think that a free group is enough. Just multiply, just multiply, just multiply, multiply. But actually, it's not enough. Okay, actually, it's not enough. Okay, something would disappear if you just use a free group construction here. Okay, so instead, what we're gonna do is even more general than free group. Okay, it's what we call the free product. Okay, so let's start with a collection of groups G alpha. Okay, so this free product don't deserve to use a multiply sign. Okay, instead we'll use a me sign. Okay, what's this me? Asterisk. Okay, so this is an asterisk. Okay, asterisk. So what's this asterisk here? This asterisk here is defined by the set containing all words. Okay, up to here is still similar to free group. You just take G1, G2, go out to GM. But the point here is where you pick this GI is pretty important. Okay, it's pretty important. So this G1 up to GM right here, right, is make sure it's arbitrary finite length. We don't have like dot with not analysis here. So not dot until infinity, not series, not a sequence here. So it's a finite length, okay, such that this GI actually come from a fixed GA alpha I. Okay. And then GI not equals to E. Yeah. Okay. So the point here is what? You might think of this word is a letter by letter, but these letter come from different group. Okay, these letter come from different group. So adjacent letter should come from a different group. Okay, so it's like a chunk by chunk. Okay, because it's not a chunk anymore because our group is closed under multiplication. You understand what I say or not? Why we can do this? Because potentially these groups are different. Maybe you think of it as a matrix group, complex group, and then SN group. These are all different elements. How to multiply together? Cannot. You just can put at side by side. But anything close to each other that is adjacent, you can compose them because it's a group. So in the end, you will left with this version. Okay, so adjacent letter belong to different group. Does it make sense or not? Should I write down an example? Can you imagine what I say? Okay, so maybe you got the XN me with maybe C then with some matrix group, right? So you get 1, 2, and then suddenly you got the identity here. Suddenly you got the matrix here. No, M is not a good group, right? So maybe we pick GLN. Maybe 2, 3 here. GL2, and then this one S2. This is a set called reduced word. Okay, how to take products is the same, concatenation. Okay. So you have heard concatenation twice in this course already. One is a concatenation of path, and then this one is a concatenation of elements of group. Another word for concatenation is juxtaposition. Okay, so you just put side by side, that's it. Okay, so you can reduce if they stay in the same group. because this is a group property, it's closed under apa? Binary operation. Okay, and reduce. So one thing you want to check is the LLC associative or not, and then what's the identity? Okay, what's the identity? Identity. What's the identity? Any identity from one of the group is an identity. Is it? Huh? Sorry? Is unique. Wait, let me think how to put this. The identity let me think. So this is juxtaposition, right? Let me think. So nothing. Should be nothing. Empty word. Seems like empty word. Why I put this line down? Should be empty word. Yeah, if you put identity, because okay, so the point here, if you put identity, if you choose identity from the group, the point is you might not meet up with the same group element, so they won't like absorb. Let me think. Is the empty word appears here? There's no empty word here. There's no empty word here, right? Because let me see. It's all
If any of
the length could be 0. Oh, the length could be 0. Then that's okay. The length could be 0. M is greater than 0. Then why I put here the identity element is given by the group? This one doesn't make sense, right? Because let's say the element I draw just now, okay, and then I put an E here, then this E is from S2, then cannot combine with GLN anymore. I don't know. If let's say I put this identity element from S2, I compose these two, juxtaposition, I just put it here only. Then that cannot combine because these two are not from the same group. I don't know. Doesn't make sense.
oh whatever.
But what? But if I put identity of GLN is all works, right? So this is an identity, or actually, let me think. Sorry, take identity from each group. Each group. Each group. How do you mean? So is this a group? Free product is a group or not?
It should be. It should be a group.
It should be a group. Yeah, I think it should be a group. So what's the problem here? So identity is given by the identity from any one of the group. So does it violate the identity is unique property? So what's the problem here?
Just as you see, you cannot put it.
The left right is not the same. Left inverse and right inverse. So how we prove left inverse, right inverse is the same like last time. So we can create. So we can do. How do we prove left right inverse? Oh, yeah. it's like so this one is identity, right? And then we can do how do you prove left right inverse is the same last time? So you start with the left inverse, right?
Actually, the
Then-
textbook
Huh?
says that the identity should be empty.
Is what? Is anti-word? Think.
Then why is GI?
Sorry?
I mean, that problem becomes why is GI not PI?
What do you mean by GI cannot be identity?
Because your definition says that.
Oh, I think I know what's the problem now. Okay, this identity is only identity for this one, right? But identity have to work for every element. Yeah. So this is actually not an identity. Okay. I think only empty word can satisfy that. Yeah. Because identity should be true for all group elements. Correct or not? The definition. Okay, so even if you put this, this is only true for one element. Right now. Yes, which definition?
You said that why you ask for that each factor GI because
What letter GI?
you that
Up, down. Yeah.
you see that GI is not E. Yeah, I mean
Why we need this? Let me think. So I think they don't want, it doesn't want elements looks like.
possible to work with them while we
Let me think. Can we do that? Yeah, actually they don't want. They don't want. I don't know why, but maybe later we'll see why. Okay. So okay, let's look at one example. Let's try one example and then see if it matches up or not. Okay. So the claim is if you do Z stars free product with Z star actually is the free group generated by two elements. Okay, so if we use the definition we had just now, what kind of thing is here? Okay, so well, 0 is in here, right? So how about think about this first? I think F2 is easier to think about. Right, so F2 could be like X, Y, and then what else? Maybe X square Y, something like that. And then so on. Okay. And then on the other side, on the other side. So you should think of this XY as a generator. No? So on the other side, you also have two generators, right? One here. Okay. So maybe you can compare the element between these two. Okay. So what do you have? So well, you could have 1, 0. Okay. And then you could have 0 star 1. Okay. Or 1 star 0. Right. Can we have 1 star 0? It says that it cannot have identity, right? So we have, oh, sorry, let's remove this first. We obviously have 1. Okay, and then 1, 1. And then, okay, maybe we should say this one is A, this one B. So we know where this one come from. Okay, maybe this is 1A. Okay, we also have 1B. Okay. And there we have 1 star A, 1 star B. But this is Z, right? We also have 2A, 2B, and then 1 star, something like that. Okay. So if these two are isomorphic, right, who should pair up with who? So maybe we also have 0 here. Do we have 0 here? We only have 1, right? Okay. Okay. Well, I guess everything. So do we have 0? We don't have 0, is it? We need to throw away the identity. Correct.
Actually, we should have the identity as empty word.
Yes. Yes.
Zero is not a read. It's a word but not a read. Empty word is a read. So actually, we should zero here as empty word. Yeah, we have that not empty word.
So sorry, say again. So the point we throw away identity is because it is equivalent to empty word. Is it what you say?
It's like
Yeah.
When you activate something with an inverse together,
Mhm.
then we
Become empty. Right.
yeah,
Instead of going back to
Yeah.
the identity.
this is identity and the word is
Okay. So that's why we throw away 0. We replace it by. Okay.
the word but not the reduced word.
Depend on how you define, right? Depend on how you define. But okay. Okay, sure. Okay, so the point we throw away 0 is kind of like we replace it by the empty word in this composition here. Okay, and then in the following composition, we won't care about the composition with, I mean the product. We didn't define product with empty as the identity because we treat it as an empty word. But also if you add in elements like this, right, you should think of it how I pair with this guy. If I write down like this, is it obvious how you know how to pair now? Sorry, 1 star 0, for example. Okay. If you add these things in, then we won't get this kind of isomorphism. You make sense or not? If I write down, you see here, there, you can compare who should map to who.
So actually, one star zero when you reduce it, it's just for one.
Oh. Okay. Wait, let me see. How do I define reduce? Where is Oh yeah, sure. Yeah, okay. So yeah, okay. Yeah. So we throw away E by saying that it is get reduced. I think that's fine. Okay. Yep. So you can see this isomorphism, no? So you send your I1 to IA to X, IB to Y, and then this one should go to X1, you know, and then 2A go to X squared, and then 2B go to Y squared, and then this one maybe go to XY squared, something like that. Match up. Okay. Sorry. 1。什么叫 1 呢？F2 F 这个 E 哈呀 empty。Okay, identity go to identity。star 是什么？那个星星这个星星三干的 star 什么？这个什么叫三干的 star？哪一个？我用哪一个？我用哪一个？ History 啊，不是这个 story，是这个吗？
书上不是，
它哪一个？
书上没有少一横。
它少一横，少哪一横？
它是五角，
少哪一横啊？这样？
对对对，
嗯，What's this？
转。
这是什么？
书上是这个，我注意差异。书上是这个。
真的吗？我没有注意到哎。But anyway，我们用这个吧，
好的。
随便啦。I think。Okay。Yeah. Okay. Maybe we'll continue next time. But another thing is a very astonishing fact is Z2 free product with Z2 is actually not finite because Z2 cross Z2 is 4 elements, right? But this thing is not finite. Huh? Yeah, not finite.
所以我认为你第一个也不应该用 Z，可能会看成 Z 光。
哪一个？
你上面那个 example 里面，你别把这个样子一会儿。
哦，放哪里？好像放哪里都不太对。放不同颜色啦，这样子，或者放一个刮胡。哦，等下被 localization。糟糕，什么东西都不能用啊！现在啊，是不是 squid 的刮胡啊？这样子，好吧，很恶心。不然我放这里啦，放这里，放这里，
哦，也可以。
放这里，放这里。放这里，这个没有人用过，我们可以用。Okay. But can you think of one thing why this is not well, okay, who guys have infinite order now? Who has an infinite order? Because normal Z2 cross Z2 only 4 elements, right? Okay, but now there's something inside here got infinite order. Maybe discuss about this and then we can finish. Yeah. Infinite it actually is a very normal, very easy example one. Just look at maybe one. Okay, just use the notation before. 1A star 1B. Okay. Because you need to understand what do I need to understand? You can actually start forever. And the thing you need to satisfy is all these things come from some G alpha is enough. Okay, and then the adjacent one shouldn't come from the same place. That's it. If they come from the same place, you just combine them. This group is isomorphic to what? This quotient F2 quotient. X square, Y square.
X square and Y.
Not really. I don't wait, let me think.
No, I mean
Not
X square
and Y
square.
Not quite. XY. XY.
X square and Y.
X square and Y square. This one.
X square comma Y square.
This one. Then this one, no, this one is the 4 element thingy, right? This is not right.
No, that's why this thing is not.
Oh, you mean that?
We did not.
You can try that. Okay, but we will review another structure on this. I will review a structure on this. Okay, yeah, maybe you can try. You try if you can show this. Okay, if you finish, please hit feedback the quiz. You can take a picture. And then I'll see you on Wednesday.